start again. So, don't really have anything to say about section 10.5 in Dummett and Foote this semester. That's on the sort of abstract homology, which I think is, it deserves more time than I could give it right now. And you really should have a course in homology so you can properly appreciate it from top to bottom. It's not a bad thing to read through it, but that section should be blown up into a course. Anyway, so this is chapter 11, which is on vector spaces. And of course, I don't think this is the first time that you've heard about a vector space, right? So, he has this wonderful, table of corresponding terms, right? M is an R module is like M is a vector space over R. M is an element of M. M is a vector in M. Alpha is a ring element. Alpha is a scalar. N is a submodule. N is a subspace. M mod n is a quotient module. M mod n is a quotient space. M is a vector space of dimension n. M is a free module of rank n. M is a finitely generated module. M is a finite dimensional vector space. M is a non-zero cyclic module. M is a one-dimensional vector space, right? Phi from M to n is an R module homomorphism. Phi from M to M is a linear transformation. M and n are isomorphic as R modules. M and n are isomorphic as vector spaces. The subset of A generates M. The subset of A spans M. M is equal to RA. Versus each element of M is a linear combination of elements of A. M equals span A. Now I've talked about some of these things already, right? But
I never thought about vector spaces like small custom.
Right. So you remember we have at the base of everything linear independence and spanning, right? S, a subset of a vector space over the field F is linearly independent if and only if for any n in n and S1, S2, Sn in S, C1, S1 plus C2, S2 plus Cn, Sn equal to 0 implies what? C1 equal to C2 equal to Cn equal to 0. In other words, a subset of a vector space is linearly independent if and only if any finite subset of that set has the property that when you take a linear combination, and I should clarify here, I do need C1, C2, Cn to be in the field, right? Okay. So if any finite F linear combination of elements of S gives you 0, it implies it's the 0 combination that gives us linear independence of S. This is a little bit different than the definition you saw in basic linear algebra because it allows for infinite dimensions. You may or may not have done that. Yeah?
Yeah.
Because a lot of times we're working in a finite dimensional context, so you don't have to do this, take a finite subset thing. You just say, you just use everything. Because if S itself is finite, then you can just take a linear combination of everything in S, But, if S is infinite, you do want to just consider finite linear combinations, all right? That's the rule.
For this V acting on F, is that just the vector space of the field F? Or what was that, just in words?
What is the, oh, here. So let's say V of F is vector space over F. So here I'm assuming that this is a field, right? The field of scalars. In the R module language, V is the module, and R equal to F, right? This is a F module. V is an F module. And what did it take for it to be a basis, you remember?
Two things couldn't combine to be another thing.
So S is a subset of V over F is basis if S is linearly independent, right? And what else? The span over F, right, of S is equal to the whole thing, right? How do we define span?
In diff geo, we define it as the vector that is like all scalar multiples of a certain vector that gives you the whole thing.
Yeah, so let's see here, span of F of the set S, right? It's going to be basically the sum. And he keeps using alphas for scalars. I guess I should too. I don't know, it's too late. Sum over Ci, I equals 1 to n of Si, such that, you know, Ci is an element of the field, Si is an element of the generating set, right? And I is an element of the natural numbers. So the span of S is all finite linear combinations of elements from your generating set S. And also, for the sake of like making theorems and stuff work, we define the span of the empty set to just be the zero vector. All right, now, so that's the basic thing, right? So if your vector space has a basis, right? If, you know, S is basis for V, right? And suppose the number of things in S is equal to n, right? Suppose it's less than infinity, right? Then the dimension of S, excuse me, the dimension of V is what?
That was the number of vectors in the span.
Right, exactly. So it's equal to n. Okay. And this definition makes sense because we prove in linear algebra that if you had two bases for a vector space, right, and they're both finite, then they have to have the same number of things in them. All right. It takes me about a half hour to prove that. There's a lot of different ways to prove that. And so for a given vector space, there either exists a finite basis or there doesn't, right? So if there does not exist a finite basis, then the dimension of V is said to be infinity. It's an infinite dimensional vector space, all right? We had a slightly more nuanced definition of rank of a module. We had the cardinality of the module was the cardinality of, if if it's free over some set A, then the rank of the module was, I think, the cardinality of the set over which it's free. So I could see there that you could have different sized infinities for your for the set over which your module is free. But here we're just saying if it's not finite, it's infinite. Okay. What else can you tell me? Well, it's just trying to refresh us on some of the basics here before I get too carried away. So the other big theorem is, you can call this I think Anton calls this the plus-minus theorem. Okay, so given the finite dimensional all right, and S a subset of V, number one, if S is not linearly independent, then can modify S to become linearly independent by removing elements of S. And you can do it one at a time. Remove an element. Is it linearly independent? Nope. Oh, remove another one. Is it linearly independent? Nope. Linearly dependent, rather? Nope. And so you just keep removing them until it becomes linearly independent. That's the minus.
Okay.
Okay?
My example for like this stuff is like really just simple. It was like R3 is just ij's and k's, you know?
Mm-hmm.
And you can't add I and j anyway to get k and etc.
Mm-hmm.
And so like, this is that's a pretty much summation of what we just said here, right? And then if you have infinite, and besides the last one, but I'm talking about these first two.
What's an example of infinite dimensional vector?
Well, I know Rn is an example of infinite dimensional.
No, Rn is n-dimensional.
Oh, I didn't think.
Mm-hmm. We'll look at examples next.
Okay.
So, but the other thing is, let me just finish this, and I'll get back to my examples. So two, if it's not linearly independent, if it's a linearly dependent set, you can delete things from it until it becomes linearly independent. All right. On the other hand, if the span of S is not equal to the vector space, right? Then if X is not an element of the span of S, then the span of S is a proper subset of the span of S concatenated with X. Sorry, my notation kind of sucks, but sorry, it's horrible. But it's an inclusion though, and the thing is, if the new one is equal to V, great, you found a generating set for V, right? Otherwise, what do? You find a Y which is not in the span of the S union X, right? And you can just keep repeating this process, always unioning with something outside of the span of what you already have. And in this way, ... eventually you can, etc. Eventually you can enlarge S to, let's say, S tilde, where the span of S tilde is equal to V. Right? Now, if you put these two things together, what does this mean? if we put these two things together, what it means is that we can take any subset of a vector space, right? And by suitably removing redundant vectors and then adjoining vectors which are not there, extend it to a basis. So this gives us the basis extension theorem. And I'll state it in an easier way. So if S is a subset of V and S is linearly independent, then there exists beta, let's say, equal to S union with, call it S prime. Well, let me state it this way. Then there exists S prime such that beta equal to S union with S prime, a basis for V. In other words, if you have a linearly independent set, you can extend it to a basis. Put a different way, if you have a basis for a subspace, you can extend it to a basis for the whole space. You okay?
I'm fine. I'm shoving in muscle space. My heart was going crazy.
Too much caffeine? Do I need to get you a doctor?
If I pass out, I'll pass out. We'll see. I doubt it.
No passing out.
I have a pretty big heart.
Honestly, I wouldn't even know where to take you.
Please don't take me here. I take my chances driving 45 minutes.
Should carry you out to my car and drive to Tuscaloosa. I'll be on the phone. Jenny, where's the hospital? I finally found my excuse to see how fast my car can go.
I'm so serious. Don't take me to the Winston Hospital.
Hey, I was beating an ambulance on the way. Anyway, okay. So, all right. What was I getting to? Oh, examples. Because I think that's probably important, isn't it? So, standard examples. My favorite, just the real numbers n-fold times, right? So this is the span of the standard basis EI. I equals 1 to n, right? Now here, EI, the jth component of it is Kronecker delta ij, right? So like E1, which is my sneaky notation for this. All right. So Rn. Now, how many? So the dimension of Rn is n. Over the reals, anyway. Let me just give you a perverse second example. If you take V as the real numbers over the field of rational numbers. This is an example you won't see discussed in a reasonable linear algebra class. Like this is sort of more the province of real analysis. Anyway, there does exist a the reals are a vector space over the rationals. All right. They're not a nice vector space over the rationals. There is no finite basis here. Okay. I can't even write the basis down for you in like any kind of nice way.
Basis because of the irrational numbers?
Well, if there was a finite basis, that would mean, okay, so fun facts about cardinality. The cardinality of a set is equal to the cardinality of the set to the nth power, and many other things. So like if you take a Cartesian product of a set with itself, well, this is only true in, okay, infinite cardinality. Okay, finite cardinality is more interesting, you know. So assuming that it's infinite, all right? Like countable, for example, the size of the natural numbers is the cardinality of the integers, is the cardinality of the lattice, is the cardinality of the rational numbers as it happens. Now that kind of blows your mind a little bit, that the rational numbers are also countably infinite.
Oh no, we did that in modern.
Okay, so that's surprising though.
Yeah.
But the thing is, if there was a basis, if the rational dimension of the reals was n, that would mean that R is isomorphic to Q to the n, which would then say that the cardinality of the reals is the same as the cardinality of the rationals, which would say that the reals have the same size as the natural numbers. But this is not the case.
Because we know, yeah.
Right? But we know that the continuum is larger than the number of natural numbers. Okay, so this is a infinite dimensional vector space over Q.
Yeah.
So your choice of base, scalar matters, right? Can I erase?
Yeah.
Okay.
Yeah, that's what we mean by like.
But of course, this stuff is not true of finite sets, right? If I have a set with 3 things in it, and I take the Cartesian product of it with itself, then I have 2 tuples with 3 things in both. That gives me 9 elements, right? So like, it's the size of S to the n power. Anyway.
We were talking about infinite sets then.
Right. So another example would be, we talked about this a lot, polynomials over the reals, right? So here you're looking at the sum n equals 0 to infinity of Cn x to the n, such that finitely many Cn in R non-zero. What's the basis for this? There's many, but one nice is the monomial basis. Well, it goes on and on, yeah? So that is an infinite dimensional vector space. That's pretty nice to work with.
Yeah.
Now, 3, of course, you can always talk about subspaces, right? Subspaces are vector spaces. And there's 2 basic ways to get subspaces, right? The one is the span of some set. This is a subspace of a vector space, right? Here I'm assuming S is a subset of V. Not necessarily infinite. Any subset. It could be infinite, it could be finite, whatever. A span is a subspace. Okay? The other way to get a subspace is as the kernel of a mapping T. So this would be, x in V such that T of x is equal to 0. And here T, I'm assuming, is a mapping from vector space V to vector space W. Let's say both over some field F, yeah? it's a truism that any subspace can either be written as a span or a kernel. And really, a kernel is, what is that? That's really the equation viewpoint. Because if you look at it, it's characterized by t of x equal to 0, right? Whereas the span is more like the parametric viewpoint, because it's a linear combination, of things in S. And each of these viewpoints has its benefits, cost, whatever. Another example I'm fond of course, is matrices, right? So if you have R m by n, so here we're talking about, m by n matrices, right? So I don't know what notation you want me to use here. I'll just do it like this, A, such that A is m by n matrix. So, of course, A is equal to A11, A12, A1n, AM1, AMN, and you can write that as the sum I equals 1 to m, sum j equals 1 to n of A ij, capital E ij. Now, if you set that equal to 0, the only way that can be 0 is if all of the aij's are 0, which shows you that the set of the big E's are linearly independent. But this equation also shows you that they span. So the basis for, the standard basis, really, for RMN has the form EIJ 1I less than 1 to m, j between 1 and n. Now, that's ambiguous, right? Because a basis is not just a set, it's an ordered set. So, to be fussy, I should really tell you which one comes first, which one comes last, So is this refreshing?
Yeah. No.
Okay. So let's take a step back to matrices, explicit matrices. Let's talk about that. What can we say there about linear independence and all these things? Let's see here. So I'll just remind you, so here's basically the theorem, let's say Gauss-Jordan row reduction, yeah? So if we're given A in R m by n, then the reduced row echelon form of A, right, is uniquely fixed by the Gauss-Jordan algorithm, right? And what we can say is that, what can I tell you about that? The number of pivot columns, right, equals the number of pivot rows All right. And that's equal to the dimension of the column space of A. I mean, I'm not saying that, really I should say this is equal to the, I really should say this is equal to the dimension of the column space of A. This is equal to the dimension of the row space of A. And these are equal, of course. And this defines what's called the rank of A. But this is the theorem. The number of pivot columns is equal to the number of pivot rows, right? And yeah. Moreover, the number of non-pivot columns, right, is equal to the total number of columns, which is n, right, minus the rank.
N is what again? The total number of...
This is an m by n matrix, so it's got n columns.
Yeah.
So the number of non-pivot columns is equal to n minus the rank of A, but it's also equal to what's called the nullity of A. And the nullity of A, what is this? Where the nullity of A is the dimension of the null space of A. What's the null space of A? What you're looking at is X in, let's say, I'm working over R, but we could just as well be over F, right? Okay? So it's X in Rn such that AX equal to 0.
This is what the null of A means?
Null of A, yeah.
Or just the dimension of the null?
Oh, sorry. This is null of A. Thank you, yeah. An important distinction to make. But there's more than this, right?
Yeah.
Because, in fact, we have the following. So, I'll write over here. So one of the things that we should notice, like big story here, is that we have a relation between the rank and the nullity, right?
Yeah.
What is the relation?
N minus rank A.
Right, but there's another way to write that, which is that n.
Equal to the nullity times plus the rank.
Yeah, rank. So rank, the rank nullity theorem. Rank of A plus, and sometimes some people use a nu for nullity, since writing nullity is a pain. So this is the rank nullity theorem for a matrix. All right. But there's more. There's more, Audric, because we also have this result that at each step of the Gauss-Jordan algorithm, we get, let's suppose we start with A, and then we go to step 1, and then we go to step 2, and so forth and so on, right? So if you're to the jth step, you can get that from an elementary matrix, the jth elementary matrix, all the way down to the second times the first elementary matrix multiplied on the left of A. So every step in the Gauss-Jordan elimination is related to the initial matrix by left multiplication by a product of elementary matrices. Those matrices are invertible. It may or may not be the case that A is invertible, but those are invertible. And of course, if the matrix is square and it's invertible, that means after you're done with the row reduction, you get to the identity matrix, at which point this eventually becomes what? Like the identity matrix is equal to the total number, whatever it is, say k of them, right? So if this is in the in the case a square, in the case that the reduced row echelon form of A is the n by n identity matrix, right? Then this happens, which of course gives us one of those many equivalent characterizations of an invertible matrix, right? Like, what is an invertible matrix? It's a square matrix, right? What you can say about it? Well, it can be written, its inverse can be written as the product of elementary matrices, which incidentally also means that A can be written as the product of elementary matrices, because if you hit this by EK inverse, EK minus 1 inverse, all the way down to E1 inverse, you get A is equal to a product of the inverses of elementary matrices, but guess what? The inverse of an elementary matrix is an elementary matrix. So he did all this stuff in your linear?
Oh, right? No.
No, okay.
I mean, like...
Some of it.
Yeah. I mean,
Because
these concepts were covered.
These were covered, and he used them to derive the rule for determinants, right?
Yes.
Right. In your homework, you'll derive the product rule for determinants using wedge products. It can be derived from the properties of wedge products. So in that homework problem, make sure you do part B first, then part A. I was looking at my solution. I'm like, ooh, I did part B first. Sorry. You should do part B first. Okay. Anyway, get into the weeds a little bit here. But the point of this was, so we have this, there's basically always, at every step, right? You can, let me just call all of this just E, right? We always have R sub j is equal to EA for some, product of elementary matrices, right? That's an invertible matrix. So check this out, right? If the sum of, let's say, Ci column I of A, I equals 1 to n, if this is equal to 0, then what?
That goes in the non-pivot column.
Well, I'm just taking an arbitrary linear combination of columns of A, okay? I didn't say it was any particular one. I'm just saying, suppose you take a linear combination of columns of A.
Yeah.
Multiply this by E. Okay, multiply it by E. Multiplying by E, bringing the E inside the summation, we get the sum I equals 1 to n of Ci E coli of A equal to 0. Oh, I forgot this calculation's sick. But fun fact, this says that column I of Rj is equal to E times column I of A, right? This is the way that matrix multiplication works column by column. The ith column in the product of these two is formed by multiplying the ith column and the right factor by the left, yeah? So this is straight up the sum I equals 1 to n of Ci column I of Rj, whatever step we're at, yeah? So maybe I should have just erased j from, let me just erase j from this. It's distracting, okay? Erasing the j. The point is that this is a row reduction of A, okay?
Yeah.
Let's drop the j, it's not relevant. Could have been any of the steps. The point is that that's still equal to 0.
The E's a matrix. It's an invertible matrix.
Mm-hmm.
So you're, wait.
But it's the matrix that transfers column I of A to column I of R.
Yeah.
Your reduced matrix.
Yeah.
What this says is that any linear dependence of the columns of A must be present as a linear dependence of the columns of any reduction, any row reduction of the matrix. This is known as.
Oh, yeah. So like if there's somewhere where you get like 2 1s or something, yeah. Like I don't.
This is known as the linear correspondence.
Mm-hmm.
So let's see how it works out in practice.
Yeah.
So if I have like 1, 2, 3, last column 0, 1, 1. My middle column is, I don't know, 1, 3, 4. All right. I'll reduce this thing. So I'll do, first of all, I'm going to subtract 2 copies of row 1 from row 2 and 3 copies of row 1 from row 3. So I've got subtracting, I got 0, I got 1, I got 1, I got 0, 3, so 1, and 1, yeah. And then, let's see, I'm going to reduce until I get to reduced row echelon form, okay? So here's my A.
1 from 2. Like that.
Oh, so yeah, subtract. My second pivot position I'm going to use is this guy. So I'm going to clear out below it. So I get, zeros, yeah?
Yep.
And then clear out above. There we go. We did the forward pass, we did the backwards pass. We are now at the end of the line. This is the reduced row echelon form of A.
Yeah. Those are linear dependent, right? Because it's not like in the first column.
Uh-huh. So what are the pivot rows? The pivot rows are rows 1 and 2, right? What are the pivot columns? Columns, in this case, 1 and 2.
Yeah, because
right.
I only have one thing in there.
But my point to you is that it is manifestly obvious, if we look at this, that column 1, rather column 2 of A, right, minus column 1 of A is equal to column 3 of A, right? Oh, excuse me. That's not A. This is.
Yes.
It wasn't. It was. This is the thing I was calling R, right? So, excuse me. R. There we go. That is here. That is just obvious from this, right?
Yes.
We can always write the non-pivot columns as a linear combination of the pivot columns. That will always be possible. All right? In other words, what I'm saying is that you can add another thing to this, which is that, column space of A is the span of what? Pivot columns. It's the span of the pivot columns.
So what happens when you get when you get an identity out of the
But
reduced row?
what I want to show you, though, before we move on, this is still true at each step. Like column 2 minus column 1
Oh, yes.
is that. Column 2 minus column 1 is that. Column 2 minus column 1 is that.
It's always like for any random matrix.
This is the linear correspondence. Any linear dependence revealed by the reduced row echelon form is present in every one of the row reductions. This is not emphasized in any linear algebra class taught, almost anywhere, but it should be because it is the most important matrix calculation. Because with this, you can simplify many, many things. My brother attributes this as the reason that we had difficulty in graduate linear, because the book it wasn't the fault. I had a very good professor. I don't know who Bill had, but I'm sure he was fine. But the book I learned undergraduate linear algebra from, Larson and Larson, I think it was, it did not have the linear correspondence. Which means every single time you're ever doing a span problem, you're just always going back and solving a system of equations. When what you should be doing is putting the vectors you're interested in, doing a row reduction, and using the column correspondence to understand the linear relation between them.
This is only for square matrices, right?
No, this is for any kind of matrix.
Really?
Yes. Let me show you. So,
like, I pick n by n matrix.
yeah.
I put any numbers in there. Whatever linear dependence pops out in the reduced row echelon, I will find throughout.
For example, was this example 2? I don't know what example I'm on. 20.
Yeah.
Okay, so check this out, right? Suppose you have the reduced row echelon form of A is equal to, I don't know, 1, 0, 0, 2, 0, 0, minus 1, 0, 0, 1, 0, 0, 6, 1, 0, and this guy. Can I do that? Yeah, I can do that. All right. And you're given that column 1 of A is 1, 2, 3. And you're also given that column 4 of A is 0, 1, 0. Find A.
Okay, so.
This is a problem I assign in linear algebra to force students to understand this.
Okay, so essentially what we have, well, this one gave us this, so that means column 1.
Right, so 1, 2, 3, that one's for free, right?
Yeah, and then.
I'll draw some blanks to fill in. Column 4 was
0, 1, 0. Okay, but how do we know which ones add up to which ones?
the
By this?
correspondence.
Oh, okay.
Because any linear any correspondence in the reduced one has to be present in the original one.
Okay, so.
That's the linear correspondence.
So that means. No, we can't. So we need to look for stuff that. Okay, so one double.
Yeah, let's start with that one.
Yeah, one double.
You just have to double the first one.
Yeah.
So that's 2, 4, 6. Yeah.
Okay, cool. And then one minus. Minus 1, minus 2. Okay, and then we have.
That one's for free.
Yeah. So this. Ooh. So this would be that one times.
Yeah, I'll write it over here. 6 times 1, 2, 3. Right.
Yeah.
Plus 1 times 0, 1, 0.
So yeah. So we get 6, 7. I mean, 13.
Mm-hmm.
18.
Mm-hmm.
And then keep it the same thing on the end.
Oh yeah, and then they're.
Yeah. Huh.
You can try it out. Stick it in your favorite computer, do the row reduction, see what happens. It's unique. It'll go back to what we started with. Guarantee it. Yep. It's not just cool. It is essential. And it's malpractice. It's linear algebra malpractice to not teach this in your class. And yet many people do not, because we have many battles in that class that we're fighting.
Maybe I'll help someone out one day.
Nah. So what's the basis for the column space of A?
What's the basis for the column space of A?
Column space of A.
Span of pivot columns. So we have, how many pivot columns do we have? We have 1, 2,
Mm-hmm.
3.
So what we do is we do.
I see 3 pivot columns.
So you do 1, 2, 3, and there's only two pivot columns. These are the pivot columns. This and that are the only leading ones in the row reduction.
Yeah.
Leading ones tell you where the pivots are. So That's it. So the rank of A is 2. What's the nullity of A?
We have 6 columns.
Yep.
Minus 2, 4.
Right, so the nullity of A, 6 minus 2, as you said, 4. What's the basis for the null space of A?
The basis for the null space.
Allegedly, there are 4 things in it. What are those 4 things? How big should they be? Where is the null space of A? It is a subset of Rn, right?
Yeah.
Now here, n equals to 6, right? So we're looking for 6-dimensional vectors, right? So here, I'll show you how to do it. What we do is we just take x1, x2, x3, x4, x5, x6, right? This is in the null space, all right? Now follow me here. So this is x, all right? And let's suppose ax equal to 0.
Ax equal to 0.
Right. So remember what we did, the row reduction to start with, to solve systems, right?
Yeah.
So what's the augmented coefficient matrix for this system? It's just what we have, right?
Yeah.
It's if I do, well, I could say this. Let me just go back to here. If I do this augmented with a column of zeros, guess what happens? That column of zeros does what? It adds and multiplies into itself. You just tack it on, right?
Yeah.
Okay. So my point to you is we know how to solve these 3 equations and 6 unknowns.
Yeah.
Because we have the row reduction right here, right?
Yeah.
So that tells me that x1, for example, is what?
1.
It's not 1. x1 is equal x1 plus 2x2 minus x3 plus 6x.
Is equal to 0.
So here's,
Yeah.
just as a guide. So we have x1 is minus 2x2. Notice the signs. Minus 2x2 plus x3 minus 6x5 minus x6. That's what x1 is equal to.
Oh, yeah. Mm-hmm.
What's x2 equal to? It's equal to x2. All right.
X2 is equal to
Yeah, x2.
minus like half. Yeah.
So we'll leave x2 alone. We'll leave x3 alone. All right. Because we're using those in our answer for x1. x4 though, that's our next pivot. We got to be careful of that one. x4 is minus x5 actually. x5 is x5. x6 is x6. And then all you got to do, pull out your x2. You got yourself a minus 2, 1, 0, a 0, a 0, 0. x3, 1, 0, 1, 0, 0, 0. Plus x5 minus 6, 0, 0, minus 1, 1, 0. Plus x6 minus 1, 0, 0, 0, 0, 1.
Oh, I got you.
So the basis for the null space minus 2, 1, 0, 0, 0, 0. 1, 0, 1, 0, 0, 0. Minus 6, 0, 0, minus 1, 1, 0. Minus 1, 0, 0, 0, 0, 1. There's your 4 vectors. We can always do this. We can always solve for the pivot variables in terms of the non-pivot variables. So an arbitrary thing in the null space of A is necessarily parametrized by the non-pivotal variables. And the vectors which appear in this process have to be linearly independent. If there was a linear dependence amongst these vectors, that would say that the non-pivotal variables had some dependence. But that's impossible. Because if they did, you could get rid of one of them. And the counting works out, right? Because the number of non-pivot variables is the number of columns minus the number of pivots, which here is 4. And, you know, another way you could look at this is it is the perp. It's the perp of the null space, yeah? It's the null, excuse me, not the null, it's the perp of the row space. If we take the row space of A, we find the vectors which are perpendicular to it, and we transpose those. That's what we have here. Because if you take these vectors, right, and you take the dot product of these with the rows of A, see what you get? Like this with that. You try it out. All of the vectors I wrote, they are perpendicular to the rows of A. This is also a useful guide. If you're just trying, like, you don't have to go through this calculation. If your matrix is small enough, you can just write down the null space by looking for vectors which are perpendicular to all your rows. For example. For example, if I had a 1, 1, 1, 1, 1, 1, 1, 1, 1, right? The null space of A is the span of 1, 0, minus 1, 0, 1, minus 1. Column space of A, span of 1, 1, 1. Now I can see that that's the null space because I can easily see that those two vectors dot product with the rows of A to give 0.
Okay.
But anyway.
What about 1 minus 1, 0?
1, 1 minus 1,
0.
0?
Yeah.
Ah, so is that an element of the span? Is that, well, that is definitely an element of the null space of A, right?
Yeah. Oh, it's a linear combination.
So suppose you want to figure out how is it a linear combination of those two. Check it out, yo. So 1, 0, minus 1, 0, 1, minus 1, concatenate 1, minus 1, 0. I'm trying to figure out how that's a linear combination of these two. So I do my row reduction, add that to that, right?